Okay, so I want to go back over some of this material on nilpotence. You see the picture here. The idea of self-composition, that you have a vector space V, you have a vector in the vector space, and you keep applying this transformation to itself. Now, if you've had abstract algebra, this maybe should remind you of the idea of orbit, and it's somewhat similar to that, but there are also some differences. So let me go through these notes. So the tool that we're using to study nilpotence is repeated composition. So you repeatedly compose a transformation T with itself. And this is a very powerful mathematical tool that's used not just here, but in other places as well. So if my transformation is T, I take T of T of T of T. And if I take T of T of T, that's still a transformation, right? Okay. Now, if T is a linear transformation, it can be represented as a matrix, which I'll use big T to represent. Then this repeated composition is the same as matrix multiplication. We've seen that before. Nice feature of matrix representation of linear transformations. So let me represent the nth composition as T to the n. So say T cubed is T of T of T. And that's a mapping. That's a mapping from the vector space V to V. Now, one first point to take in is that the range of T squared is contained in the range of T, right? So that's not immediately obvious, but it's not too hard to see. This is because the range of T squared, how do you get T squared? Well, you take a vector in V, you apply T to it, and then you apply T again. So the range of T squared is the range of T applied to vectors in T of V, right? Let me just diagram that a little bit. If I'm going to do T squared, right? If I start with V, and then I take T, and then I take V again, right? All right, now the range of T squared is going from here to here, right? But if I take T operating on all the points here, it's going to go to a subset of V here. So the points that end up over here are simply the action of T on this subset. This subset is contained in V, so it will lead to a potentially smaller set in the final codomain. Okay, so that's why the range of T squared is contained in the range of T. All right, and a similar reasoning, the range of T cubed is contained in the range of T squared, and so on, right? All right, so that's the first important point here. We have what he calls a decreasing chain of subspaces, or chain of decreasing subspaces. Now, what we know about vector spaces, that if you have a subspace, a proper subspace, it must have a smaller dimension, a strictly smaller dimension, right? If I have a 10-dimensional subspace, 10-dimensional vector space, my subspace can be at most 9 dimensions if it's a proper subspace, if it's not the entire space. Okay, so if I have a decreasing chain, since the subspaces have non-negative integer dimension, the chain must stop. Right? If I start at 100 dimensions and I'm going down at each step, the chain of steps can only be at most 100 long, because eventually the dimension will have to go down to 0. On the other hand, if two successive subspaces are the same, then they must be the same for the rest of the chain. What that means is, for instance, if the range of T is the same as the domain, then when I apply T again, I'm applying it to the entire space V, right? So for instance, if I add another one here, and this subset is the same as this subset, right? If those two subsets are the same, then that means that the image of the subset will be the same. Now, the mapping might not necessarily be the same because you're composing it twice, but all the points in this set will map to points in this set. All right, so you have a decreasing chain of subspaces, and the chain stops at some point. It could stop at the 0 vector, which is the trivial subspace, or it could stop at a non-zero subspace. Okay, so that's the idea. If any two successive subspaces are the same, they must be the same for the rest of the chain. All right. And so if the chain shrinks, the dimension decreases by at least 1, so the chain can have at most length n if V is n-dimensional. Okay, so that's the background for what we're trying to do in understanding nilpotent transformations. Right? So in this case, we've been looking at this from a subspace perspective. We're just looking at the domain and the range of these transformations. Now I want to look at an individual perspective. What is this doing to individual vectors? Okay. Now, I'm going to kind of do my argument a little bit backwards from what he's doing. So consider a block diagonal matrix where each block has zeros on the principal diagonal. Says one. This should say ones, not zeros. Ones. Okay. So let me just do a simple example here. What do I mean by this? It's a block diagonal matrix. So I can divide the matrix up into blocks. Okay. So I should say where each diagonal block, right? Not each. Okay. All right. The off-diagonal blocks are 0. So I'll just, to write this all out, this would be a block of zeros. Let's say it's 3 by 3, so it's a block of 3 zeros. Let's suppose this one is also 3 by 3. Okay. Now, the form of this matrix, as I said, it has only ones on the principal subdiagonal and zeros everywhere else. Okay. Here also, ones on the principal side diagonal, zeros everywhere else. Okay. Now, so I would abbreviate this way, right? I just abbreviate this entire block is 0, this entire block is 0. I would say this as 1, and then this is 0, 0, and this is 1. So this is just a shorthand way of doing the same thing. All right. Now, if you apply this matrix to itself, so if I call this T, if you apply this matrix to itself, you will find that it's nilpotent. All right. Now, when I do a block diagonal matrix multiplication, in fact, these blocks are not going to mix. So if I just look at one block, you can see what happens. If I take this matrix here, ones here with 0, 0, and I multiply by itself, ones here and 0, 0. Now, what's going to happen? Let's just look at the first column. If I take the first column, you see that the first non-zero entry in the column is in the second row. So it's going to pick up the second column here. So in fact, instead of having zeros on the ones on the subdiagonal, that's going to be a 0. I'm going to put the 1 down in the second subdiagonal down. Okay? Right? So whereas these ones were on the subdiagonal, so this 0 is on the diagonal, right? If I multiply this subdiagonal matrix by itself, I'm going to push the subdiagonal down by 1. Okay? So, and if I continue, then if I keep so I can say it this way. I can say each time I multiply, whoops, let's see if we can do this. So each time I multiply the matrix, I will push the non-zero subdiagonal down by 1, right? I encourage you to try some examples to see how that works. Okay, so a matrix that has this form, that has ones on the subdiagonal, is nilpotent. In fact, any subdiagonal matrix will be nilpotent. You can work that out. But in particular, this type of matrix is nilpotent. Okay. Now, I could represent these matrices in terms of strings of elementary basis vectors. So he talks about strings. So here's a simple example where you have strings. Now, if I label these, if I have my basis is E1, E2, in this case, it would be up to E6, right? Now, what does E1 go to? Well, if I multiply T by the vector, I'll just write it here. So if here, I'll do it over here, right? If I let's just take a single block, okay? And I multiply that by E1. All right, what's going to happen? Well, I'm going to pick up the first column of the matrix. So E1 will actually go to E2. Right? Now, what does E2 go to? Well, E2 goes to the second column of the matrix, which is E3. Now, what does E3 go to? Well, E3 goes to 0. Okay? And the same thing with the subdiagonals. E4 is going to go to the fourth column of T, which is E5. And if I apply the matrix to E5, it's going to go to E6, and it's going to go to 0. So here you can see how these strings work in a very simple case. Okay? All right. Now, so this is a case where we have this simple form of a matrix. Now, suppose we take matrices that are similar to this matrix. Okay? So suppose I take, let's call it T prime equals P, T, P inverse. And let's suppose T is nilpotent. So that means, say, T to the n is 0. Okay, now what about T prime to the n? And here you have this telescoping trick, okay? P, T, P inverse, and you raise that to the nth power. So what do you get? You get P, T, P inverse, P, T, P inverse. This is this trick that comes again and again and again, not just in linear algebra, but in algebra as well. And you can see that the P inverse and the P's, those pairs cancel each other out, right? All the intermediate pairs of P's and P inverse cancels out. So what you get is P, T to the n, P inverse. But T to the n is 0, so that's just equal to 0, okay? So a matrix that's similar to a nilpotent matrix is itself similar, okay? Now, suppose you have, what happens to these chains if you do this similarity? Well, what happens to the chains? This is like a change of basis, right? So remember that under the similarity, well, let me turn back to blue because it just looks nicer. So under the similarity transformation, what do we have? Well, we can have E1 will go to a different basis vector, beta 1, E2 goes to beta 2, and so on. Okay. So what happens are the new chain, the chain for T prime, will just be similar. You'll have beta 1 goes to beta 2, goes to, I'm sorry, here in this case it would be goes to beta 3, goes to 0, and then here it'd be beta 4, goes to beta 5, goes to beta 6, goes to 0. Okay? So the point is that if you do have matrices of this similar form, you can easily see how chains are formed. But if you have a matrix that's similar to such a simple matrix, you still have chains in the very same way. Now, it turns out that every nilpotent matrix is similar to a block diagonal matrix of the form described above. Okay. Now, we know that similarity allows you to change matrices into matrices of very different forms. Now, I'm not going to go through the proof of that, but that's really the basic idea, that any nilpotent matrix really looks like this type of block subdiagonal matrix, and just all you have to do to get your matrix is do a similarity. All right. Now, one of the problems is if you want to find strings for a nilpotent matrix. If you find the string, then you can find this change of basis to turn it into this form. So it turns out he details a method for finding strings, and I think there's some problems for this. So the number of strings is the number of eigenvectors, right? Each eigenvector will be the end of a string. Now, if you just have a single eigenvector, now, so when I say these are 0 eigenvectors. Now, 0 eigenvectors is the same as a homogeneous solution, right? T of tx equals 0, right? That's a 0. Since that's tx equals 0x, that's a 0 eigenvector. So the number of strings is the number of 0 eigenvectors. You can see in this matrix here, I actually have 2 0 eigenvectors, E3 and E6. Those are my 2, 0 eigenvectors. Okay, so what you want to do is trace backwards. Okay, now this longest string is going to be the index of nilpotency. Nilpotency is the power of n such that t to the n equals 0, smallest power of n. That gives you that result. Okay, so those two facts actually give you a lot of information already, right? So this tells you the number of strings, and this tells you the longest string. So that really cuts down on the options. All right, so we can, if we start the process by finding all the eigenvectors, which are the homogeneous solutions, and suppose these are v1 through v2, etc. Okay, all right. Now, at the next stage, we want to go to all of the vectors that map to these homogeneous vectors, right? So we want to find all solutions to Tx equals k1v1 plus knvn. Now, the way you do this, if you're wondering how to do this, if I say Tx equals k1v1 plus knvn, right? k1v1. So how do I solve this? I want to solve for the v1 and vn are given, the k1 and k2. So this is for k1, k2. Okay. All right. So I want to turn this also into a linear equation. Now, if I write t in this way, if I write t as a set of columns, let's call it, I guess I'll call it tau 1, tau n, right? I can write this equation as tau 1 x1 plus tau 2 x2 plus tau 2 x2 plus tau n vn to xn. And then instead of writing this on the right-hand side, I'll write on the left-hand side. And I'll write it this way, minus v1 k1 minus vn kn equals 0. I'm sorry, I should do it the other way. In fact, instead of writing it this way, let me write this the other way. Sorry. Right? Because this linear equation, Tx, is a linear combination of the columns. Okay? The columns of x, the columns of t are t1, tau 1 through tau n. So I should write this as, so Tx equal to k1, or let's just write it this way. Sorry, crossing out a lot here. Tx minus k1 v1 minus kn vn equals 0. That's the same thing as writing all these columns, tau 1 through tau n, this linear combination of columns, and then I also have v1, then I have minus v1 and minus v2. I add these two to my matrix. I augment the matrix. And this is times x, and then I'm also solving for k1 and k2 equals 0, okay? So I have another homogeneous equation that I'm trying to solve, okay? And I should get more solutions because I have more variables, okay? I may have to get the same number, or I may not, okay? All right? So I'm solving this new homogeneous equation with some added variables. Right? Now, suppose this has linearly independent solutions, v1 prime, v2 prime, etc., that are not in the span of the eigenvectors. You may pick up some additional solutions. And those are going to be, for instance, here, this E2 maps to E3, right? So that would be an additional solution of this new equation. Okay, so I'm going to pick up some additional vectors. Okay. All right. Now I have my eigenvectors, and I have these additional vectors, and I need them to be linearly independent. Okay. So next, find all. Now I add these vectors here to my eigenvectors, and I solve again another homogeneous equation. Tx equal this linear combination, larger linear combination. Okay. So this may or may not give me some new vectors. It will give me the vectors in here already because these will all be homogeneous solutions. That may give me some new vectors. So we keep on going until the solution set does not increase, and this will actually be the index of nilpotency. Okay, because eventually want to get all the vectors. So you're going to have to take the number of steps. I should say the number of steps Okay. Okay. All right, now, the final vectors that you get are the ends of the longest chains. And then work your way forward to find the rest of the chain. And then the shorter chains can be found similarly. Okay, so that gives some idea of how you can find chains for these nilpotent matrices. Now, this is only going to work for a nilpotent matrix. It's not going to work if the matrix is not nilpotent. So that's why you should check first that the matrix is nilpotent by multiplying by itself and seeing if you get 0. Not all matrices are nilpotent. And in fact, the next section is what we are going to talk about, how you deal with non-nilpotent matrices. So from this, we can see if a matrix is nilpotent, then all the eigenvalues are 0. All right, look at the matrix here. The only eigenvalues of this matrix are 0. Think about taking the characteristic polynomial here. So the characteristic polynomial is of the block subdiagonal matrix is going to be, well, you just put x on the diagonal, so it's just going to be x to the n. There's, right? Because when you take the determinant, when you put the x on the diagonal and take the determinant, because it's a matrix that has a 0 on the superdiagonal, the determinant is simply going to be the product of the diagonal entries. Okay, so that means the characteristic polynomial is x to the n, right? So that means that the only eigenvalue is 0 because the only root of this is 0. Okay, all right. So this can be seen also by contradiction. If you had a non-zero eigenvalue, there's no way that the matrix could be nilpotent, because if you keep applying the matrix to that non-zero eigenvalue, you will continue to get a non-zero result. So there are two ways to see this. So if a matrix is nilpotent, all the eigenvalues are 0. So this is a very special kind of matrix. Okay. Now, proving the converse is difficult. Okay. If I want to prove that all the eigenvalues are 0, then the matrix is nilpotent. That's a more difficult proof, and I'll talk about that in the next video. All right. Thanks for watching.